1, 2, 3, 5, 6, 6, no more than 6. 7, 5, 3 more. All right. So, welcome to the semi-last lesson of probabilistic robotics. I mean, we will have another question time on 22, and then I would say that the next step is to do the exam. So, topic of this lesson is to present the projects and also the rules for the exam. Okay? So, as you know, for doing the final verbalization of the exam in the system, I need to you to do a project chosen between those that we provide here, or also an individually selected project if you have something in mind that you would like to do anyway. Importantly, the projects are individual, so we removed the possibility of doing the projects in a team. The way you will hand in the project and also to receive remote assistance in case you need is by setting a Git repository, which should be private but shared with us, which are the staff. The staff is Barbara, Tiziano, and me. For bookkeeping reasons, you will not be admitted at the exam if you do not choose a project first. Then, if you don't like the project or whatsoever, you can always change it. But this is mandatory for us because otherwise we make mess with the bookkeeping and we don't want to do so. So, just choose the project if you want to do this exam. How the project works. We provide you with an explanation of the project, the ground truth solution, because your project will consist in a program that will parse some data, will read some data in the typical format of a text file, and provides an answer, which is the solution of a system, which is a map, a trajectory, something. And to develop a project, we provide you with a ground truth so that you can debug the ground truth solution, and with and without noise, and with some data. Next. Sorry, it seems that okay. It seems that YouTube kicked me out. Okay, and with some data. Regarding the evaluation, how will we decide if a project is okay, we will run your system on data different from those that we have given you for developing it, right? And if the solution is reasonable, then the project is a pass. We will also have a look at the code a little bit. With the project, you might win or maybe even lose plus minus 1 point, 1 point, right? So it's a small grade adjustment with respect to the mark that you will score at the exam. There is also a special case. There are situations that require an immediate registration of the exam without having done the project. This has been the case for some Erasmus students that did not finish the project in time, in the time that they were here. And to make the things even, we decided that like the project or being able to do stuff is an important thing of the important aspect of the course, and therefore these people will be penalized with 4 points, so -4 with respect to the mark of the written exam. If they don't hand in the project and they require to verbalize, because normally the project is mandatory, but if for bureaucratic reasons they don't manage to finish at the same time, then well. At the same time, we simplify the project so that to allow you to finish in time, in a reasonable time. So this should nearly never be the case. Okay. And then we come to the projects. They are stemming from real life examples or real life situations where that we encountered in our research and developments. The first one, this is a new entry, is the so-called beacon calibration. So the idea is the following. There are these indoor GPS systems that are typically based on ultra-wideband devices. I have one here, but I don't want to climb the ladder for taking it. These are small devices that are able to communicate with each other. And in some way, you're able to determine the round-trip time of a message between A and B and between B and A. So indirectly, you're able to measure the distance. And that's all you get from these devices. So some of them, they also have an accelerometer that tells you the ground, but on average, you just have the minimum necessary is just the distance, right? And the idea is that you take a bunch of these devices that, of course, are active, so they send the IDs to each other. These devices are able to measure each other distance, so the distance between me and the next, or those that I have in range. And what you want to determine is the absolute arrangement of these devices. So, like, you spawn them in the environment, they start talking to each other, and eventually sending the data to a base station or so, all these relative distances. And then you want to say where they are in the space. It's not a complicated problem. And this is the first project. Of course, after this presentation, we will have a question session. So we will have projects, a question session, like an exam sample, and then a question session. Project number 2, this is nearly obvious, it's a big success in the selection, so it's one of the most selected projects between the students, and it's to be deep bearing only SLAM. You have already done it with the Kalman filter, but you have to do it with least squares in this case, okay? Because you have done it with the Kalman filter, you have done it already, and so you do it the other way around. So the idea is that you have a robot equipped with odometry moving on a plane, and this robot is capable of sensing the relative angle of certain landmarks, which are point landmarks put in the environment. Okay? So project number 2. Not much to say. Also in this case we provide you with the ground truth, with the input data, and so on and so forth. Second is the dual of the previous problem. So we have a 2D range-only SLAM. So instead of measuring the relative angles to the beacons, this time you measure the distance between the robot and the landmark. Okay? Landmarks are points. If you have questions, write them in the chat and I will answer. Write them immediately, because in this way I can answer despite the latency. Then we come to a project which is a little bit more interesting, but this year you have all the tools and all the means to do it, which is implementing some sort of visual odometry. What you will receive are the camera parameters, of course, and then you will receive a sequence of image projections, where each point of a measurement of an image, each interest point, is characterized by two coordinates, UV, which are the projections into the image, and an ID which uniquely identifies the landmark that is visible by that point. Okay, so you have a collection of these images, and that's it. You might assume that these images are acquired in sequence. So in every image you will observe a substantial amount of the landmarks that you have seen in the previous image. What we want to have as output is the trajectory of the robot, or of the camera in this case, and the location of the 3D points. Now, you can do it as all other projects, like with a copy and paste of blocks of this course. So the idea is that you have to do a little bit of bookkeeping, but you start registering the first pair of images. You take the first and the second, and then by using the epipolar geometry that we have seen, because I've provided you with even code for determining the relative transformation between two images, assuming that you know the correspondences, then you know the relative transformation up to a scale. You decide a scale, because you can't observe the scale in pure visual odometry. You say, let's say that the translation between the two is 1, for whatever reason. And once you have that, you can triangulate the set of points that are mutually observed by these two images. And then you have your initial constellation. Then when the next image comes in, we can do a posit, which you have seen with Tiziano, only that in this case is even simpler because we have the data association given, and thus retrieve our relative transformation with respect to the constellation of points that we have created in the previous step. But if we would just do posit all the times, posit is projective ICP, after a while we would lose our constellation of points, and then we would not be able to track the camera anymore. So what we have to do is to keep track in this new frame about the landmarks or the projections that have been seen before, but have not yet been triangulated. So the open points, because if I see a point just in one image, I can't triangulate. So I mark this observation as pending, and then when I re-observe the same point from another camera, I can say, oh, triangulate between the previous position and the current position path. And in this way you augment basically this constellation of points as long as you progress during the exploration. And that's it. And at the end of this story, you will have a constellation of points and the trajectory of the robot, which is the result of all the repeated runs of posit, one for each frame, projective ICP, one for each frame. Not only, you will also have an association graph, because you know from which pose, which landmark you observe. It's given in the identity. And also you have a reasonably good initial guess. So at this point you could cast a global optimization problem that you have already in the software pool, which is a piece of total BA, of total least squares, that would then run a final refinement on the trajectory, on the whole trajectory, by minimizing the reprojection error of each individual point. Okay? This is another project. It's a little bit more articulated, but still doing it step by step. If you have run the code in the exercise and practical sessions, it won't be excessively hard. Then we have the fifth one that takes inspiration from popular robotic vacuum cleaners, and it's a planar monocular slam. Also in this case, the data associations are known. The game is the following: we have a robot that is moving on a plane and observes through a camera the world. We assume that this world is consisting of 3D points, and the robot senses through its camera the projections of these 3D points onto the image. Each point comes attached with an ID. Each observation comes with an ID attached. So the input is basically the same as in visual odometry, with the difference that in this case the robot is constrained to move onto the plane, right? Therefore, the camera will be mounted on the robot in a certain position, which is not the origin of the robot itself. It will be in a certain location, like a little bit forward in general, right? And also we can profit from an odometry, because this machine has an odometry into it. So we know our input will be consisting of the dead reckoning, which is the odometry, and a stream of point projections with ID, like in the previous example. Plus we know the camera parameters, which are the intrinsics, so the K matrix, and the extrinsics, which are the camera position on the robot. And the output will be a trajectory and a map. The points are in 3D, right? My suggestion for doing this exercise, or this project, would be to bootstrap the system by triangulating the initial set of points with the odometry. Yes, so we can get rid, thanks to the odometry, we don't need that much anymore the epipolar geometry to bootstrap the system, because we know our relative motion and we can directly proceed with the triangulation. Only that we would like to do the it's not an odometry, it's a real slam, so we want to optimize the map as the new measurements come in. Okay? This more or less concludes the proposed projects. For all projects, we don't require you to use C++ at all, and it's in our interest that you do the projects in the quickest and most autonomous manner possible. These projects are not meant to be extended to thesis, so to do the thesis with me, which I'm happy of, you do the project, you close the exam of probabilistic robotics, and then we start talking about the thesis, okay? Which will be something different, but this is restricted to the evaluation of the exam, to get it done, to get it quick, and to get a high mark. To get a project, you will have to send an email to these two folks, using the subject in the slide, writing the student ID, and waiting for instructions. And then you will be contacted soon with the data set and with all the material you need to conclude the project. Okay? If you have questions, write them in the chat. There will be also a Zoom session at the end. If meanwhile Barbara or Tiziano want to make a meet or make a Zoom for later, the stuff is well seen. Meanwhile, I'm waiting for questions that you write in the chat, right? Is there anyone? No. How long? So how long, Luca asks, how long do we have to deliver the project? Open-ended. Open-ended. So there's no... Yes, yes, Martina. You just like have to ask for the project so that you are in our system. And then we know that you are a student of probabilistic robotics, and then you can take your time to finish the exam. It's a purely bureaucratical issue for us to have you in the records. Other questions? Do you have questions on the projects themselves? No. Okay, then we can go on, and if there are no more... Excellent, thanks, Barbara. If you have no more questions, I will now take these two homeworks, these two examples of exam that you have in the repo. If you go into the repository of the previous year, there is also the solution for the exams of January, I think, and maybe February. So you have 4 examples. And then we'll go to the mid session. I answer to Martina. No, Martina, the projects work that we will have, let's say, once a month, whenever we have a critical mass, but more or less once a month, we will have a session to discuss the exam. It's somehow disconnected from the exam session. Okay, but at least there must be a certain critical mass. So we might have, let's say, 1 day in a month or 2 where we process the things. Yeah. Francesco, you can choose the project you want. There are no constraints on that. Otherwise, it would be... Francesco asks, can we all choose the same project, or do we have all to take different projects? In principle, everyone can choose the very same project, but it's less cool to me. Also because, you know, like the more people are doing the same project, the more the probability that they exchange knowledge, so to say. But I'm interested that you do the project yourself. And then it would be unfair to do an assignment first comes, first served. So you can choose whatever you like. Other questions? No other questions, I assume. Okay. The projects, the slide of the projects is not yet on the web page. I will upload on the repo. I will upload it after the question time, because maybe there is some clarification that I need to add to the slides based on the questions that you will make or more likely not make. All right, so we go to the folder, your folder, no, exercises. We go to this, and we will focus on the first exercise. Fit the circle. Okay. So the idea is, normally the test is consisting of 3 exercises, 3 questions. Normally, this year we will also introduce a 4th question, and the 4th question will be on a practical. So we will ask you something on one of the practicals that we have presented you, because normally we use the practical to introduce problems in probabilistic robotics that in other editions of the course are presented as theoretical aspects. Like, we'd rather prefer to make you doing these things so that you understand them fully, but in theory they belong to the part of explained stuff. So there will be a 4th question where we will ask something about the practical. Of course, not write me the octave code of something, but apply the methodology to this exercise, what is important here, what is important there. And if you have done the practicals and if you have run the code, then this will be a gift question. Now, normally the tests are composed by a question of theory for which you have, let's say, half an hour, and you hand in this question of theory. Then, after this half an hour, the true written exam with the exercises starts, and it's consisting of 2 or, in this case, 3 questions. Okay? In this, typically there's one topic which covers filtering and another topic which covers the second part of the course, so least squares. There might be some data association in the middle, but as usual, the topics might be also intermixed. In the previous edition of the exercises, I was commenting on the filtering part, so now I'm commenting on the ransack/least squares part. In this exercise, I will ask you to fit a circle by using ransack. So the scenario is the following. We have a set of points in the plane, many of them, and some of these points belong to a circle, and some others don't. Okay? And we would like to find, between this set of points that we believe contain a circle, to find which one actually pass through this circle. And the question is like, first question is, approach the problem with ransack by determining the parameters to be fitted, by defining a minimal solver, and by defining an error function that is able to determine the inliers, the outliers, and potentially also to refine the final solution. Then there is the question 2, in the same exercise, that says, given a set of inliers and an initial estimate, formulate the least square problem to optimally refine the parameters. Now, if you are a little bit smart, you realize that the error function that you use to determine the inliers and the outliers is basically the very same error function that you will be using for least squares. But in addition to that, I ask you also to formulate the problem, which typically means tell me the dimension of the Jacobian and tell me the characteristic, the outer characteristics of the least square problem that you're gonna implement in theory. And then there is the question 3 that you can answer also by looking at the theory. Assuming that only 10% of the points belong to a circle, how many rounds of ransack are needed to compute a solution with a certain probability? And this can be easily answered whenever you know how many points do you need to minimally fit a circle. Now, solution. Question 1. Define the parameters to be fitted. Parameters. How would we represent a circle of a certain radius? How many numbers do we need to represent a circle of a certain radius in a plane? Well, trivially, you need the point, the center of the circle, which we call C, and also you need to know the radius. If I give you these 3 numbers, then you're all happy because you can draw finally a circle. You can open your compass at radius r, and then you can put the pin of your compass into the center and turn the compass. The compass, I don't know if compass is boussole, I don't know what's the English name, but the tool for drawing circles. Minimal solver. How many points do I need to define a circle? One? No. Between 2 points, well, I can pass infinitely many circles, because if I see these 2 points, a circle having this radius passes, and then a larger circle, and so on, like a lot of them pass. So in theory, exactly, we need 3 points. So our minimal solver will be functioning with 3 points. And then designing the minimal solver, well, that's the way. Let Pi be a point in a circle. Okay. Now, the equation of a circle should verify this this constraint, this term should be equal to 0, because this means basically that the distance between the point and the center to the square is equal to the radius to the square. So this is the condition for which a point, this set to 0 is the condition for which a point belongs to a circle. So we could manipulate this equation, and if we develop the square, we have the square norm of the center plus the square norm of P minus 2 times the product C transpose times Pi, just like by developing this norm over here. Okay, and this is our first step, to construct the minimal solver. Then, if I have 3 points, P1, P2, P3, the circle that the parameters C and R that identify the circle are those that simultaneously satisfy the 3 equations for point 1, point 2, and point 3. So therefore, also these equations. So to solve for this circle, we will have to write down a system of equations telling that the parameters should satisfy all the constraints introduced by the 3 points, for the first point, for the second point, and for the third point. Okay? And this is our initial system of equations. Magically, we might see that this system is a little bit complicated, because we have C, our center, to the square, which would then develop in a polynomial system of equations. But if we observe that by subtracting the second equation, so this one over here, from the first, subtracting the first equation from the second and the first equation from the third, we might end up with 2 equations where we deleted the radius, because if we subtract the radius from this radius here from here, then the radius goes to 0. And also we eliminated the center, because if we subtract to this element, then the center goes away. So the center squared. So we end up with equations in this form, where we have 2C transpose times P2 minus P1, 2C transpose P3 minus P1 minus the difference of the square norm of the points. Nicely, this denotes a system of linear equations, because if you put the transposed here and the transposed here, and you move C to the right, you will figure out that this object here becomes a matrix multiplied by C. And so this is then a linear system. Being a linear system, we can solve a linear system in C, and we determine therefore the center. The radius still needs to be found, but once we have the center, we can simply put the center into this equation over here and determine the radius. Okay? And in this way we have defined a minimal solver for circles. Cave, if I choose 3 points, if in my constellation of points I choose 3 points which are very close, well, if I have a little bit of noise, my circle will be really dirty. So it's kind of wise to choose 3 points where to calculate the minimal solution that have a minimum distance between each other. So in this way the circle will be well defined. If you have all the points closer, 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 then the noise dominates. Okay? And we are done. So we answered the first question, the second question, the second sub-question of question 1. Then the third one is define an error function to determine inliers or outliers, because with Ransack, with my minimal set of correspondence, I compute a candidate solution. But then in order to score this candidate solution, I have to see how many of my data points are conformant to this solution, how many of the data points support the solution. And to this extent, I measure the difference between the model calculated with the minimal solver and the point. So I could simply say that the consensus, the error of a generic point with respect to the calculated circle is the distance that this point has from the minimum distance that this point has from a point on the circumference. So if this point will, the distance between a point P and the center is exactly equal to the radius of the circle, then I have a zero error. In contrast, if this distance is higher, I would have an error which is proportional to the distance itself. Okay? And I might decide, given a specific circle, to regard as inliers all the points that fall in a certain donut around the circumference of the circle. A donut of thickness T, which is our error threshold. Funnily, this error function over here is also an error function in the least square sense, that it's zero when the model is perfect, and it increases when all the points support the model, and it increases when the points when the points don't support the model, because they would go away from the circle. Therefore, a solution for question 2, which was asking to draft a least square solver, well, it's easily given, because the state is the state we want to estimate, and in this case is also a Euclidean state. Is like the center and the radius of the circle. The error function is the one that I use to evaluate the inliers, and the Jacobian will be an object which is as tall. The Jacobian for 1 point will be an object which is as tall as the error, so it has dimension 1, and it will be as wide as the state. So it has 3 columns. Okay? And this is an example of Ransack. And then there was the question 3, but the question 3 is easily answered by looking at the theory we have figured out that this is the number of rounds that we need to have success with probability P, assuming that the minimal solver, that the number of data points is n equal 3, and our inlier ratio is 0.1 W. But of course, it's sufficient that you write down this equation and you tell me what is what, and you have answered the exercise. Okay? Questions on this exercise? If you want, write them down. Otherwise, I will go to the next. No. Other exercise. This exercise is called Map the Stars. Since the exercises have a solution and you can look at the solution yourself, I invite you to look at the solution of this exercise by yourself, and in this time I will present you with a variant of the same exercise where, however, I delete this sentence. Okay? So, makes sense, so that you have one more variant of the exercise where to play with, while the old one you can look by yourself. So, the scenario of Map the Stars is the following. We live on a sphere, on a ball, right? It's not really a ball, it's a little bit flattened, but imagine it's a perfect sphere. And by being on the surface of this sphere, we could observe points which are infinitely far, which are also called the fixed stars. Okay? And we have a mechanism, so to say, to identify which star is which while we observe these stars. Of the stars, we just measure the direction. No? So if we sit on the surface of the Earth, we sit on the surface, we look at the sky, and we are only able to tell what is the azimuth and the elevation, the azimuth, so how tall is the star with respect to the horizon, and the azimuth is the orientation of the star, so where I have to turn to see the star in front, and how much I have to bend my head in order to put my pupil right in the direction of the star. So we can only observe azimuth and elevation of a star with respect to the point in the surface. Okay? This is our input. So we go around, we look at the stars that are perfectly identified, right? So we know which one is which, and for each star we don't know how far they are, clearly, but we know in which direction we're looking at. Direction expressed, for instance, in terms of azimuth and elevation, so with respect to the crust of the Earth, okay, which is just a direction. Okay? And in contrast to this exercise, where I was also giving you an odometer that was measuring your motion between one position and the next, in this formulation that I'm giving you, you don't have any sort of odometer. And what I want you to do is to determine, while you move in this world, or you observe repeatedly the stars, I would like you to construct a map of the sky and define your positions, so the position from where you observed the stars on the Earth. Okay, so it's a variant of a landmark-based SLAM, where the stars are landmarks and your position on the Earth is constrained to be on a sphere. Okay. The first question is like, formulate this problem as a least squares that computes the trajectory of the robot and the position of the stars as azimuth and elevation, or any other equivalent measure, for instance, a direction vector with respect to the position of the robot. Okay? And we want to define the state, the measurements, the prediction function, the error function, and also the size of the Jacobians. So now, given that it's a new exercise, I will have to write. Now, hopefully the light conditions will be assisting me. If you have questions, please write them down. Okay. Hopefully it's visible. Let's start. A good start for these exercises is always, to the left. Try to compensate for the skew, but it doesn't really work. When I do these exercises, it's always very good to do a drawing of the situation. So the situation is that I have a robot that moves on a sphere. This is the Earth, okay? And a robot location will be characterized by a reference system. Well, this is the z vector with respect to the center of the Earth. Okay? This is my tiny little robot that can move on the sphere. Of course, being this the z vector, it can also rotate. So you can also rotate on the spot. You can also rotate along this axis over here. Okay? Very good. And then there are the stars, which are very, very far, for which basically I just observe a direction. Now, you might consider one thing, that given that the stars are infinitely far, the fact that the robot is at the center of the Earth, or it's on the crust, doesn't really change a lot in terms of measurement, because the stars are far. So these, I don't know, 6,000 kilometers between the center of the Earth and the crust are really nothing with respect to the distance from the closest star. Okay? And we have the stars, here, which are far. This is far. Okay? The stars as well are represented like as directions on a gigantic sphere which encloses my planet. Okay? What my robot sees, for instance, from this location, is the direction at which it observes this star. So that will be in its own reference frame. It will see the star nearly close to the z vector. So it will observe this direction over here. Okay? Is it visible, guys? Okay, now let's think a little bit about the domains of my problem. So what I want to do is to construct, to determine the directions of all possible stars by only observing a little bit, and the locations of my robot that will be moving on this planet. Like, for instance, this one, and so on. Okay? What I have to do that is just the observations of the stars. Now, let's define the state, the elements of the state. Clearly, the element of the state has to comprise the positions of the robot and the position of the stars. Now, please write down how would you represent, what is a position of the robot in this system? So we follow the methodology, the state. How would you represent a robot position in this universe, in this problem? Robot position, which we call XR, belongs to which domain? Andreas has spherical coordinates. Spherical coordinates is almost right, because spherical coordinates doesn't tell you the twist. I mean, if you are in a certain location of the Earth, you can also rotate on yourself, right? Now, yes, so spherical coordinates are two angles, right? And then if I add another angle, what do I get? SE3, Martina says SE3. SE3 is a little bit too much because my robot moves on a sphere, right? So I cannot span the entire, I cannot jump on the surface. We're almost there. Now, remember that in order to qualify my state, I can also choose any arbitrary representation that with a little bit of calculation, latitude and longitude of a position, yes, but that's another element that we need. Yes, it's a 3D rotation matrix, right? Because if I sit in the origin, right, with the rotation matrix described this way, for instance, well, my point, including its twist along the z-axis, will be just obtained from this rotation matrix. Just the translation vector will be obtained by taking the x-axis and multiplying, taking the z-axis and multiplying the z-axis by the radius of the sphere, and then I will end up here. So the robot positions are SO3. Because I can express my position on the cross as the position in the center of the Earth, just projected along the z-axis by the radius of the sphere, and if I am rotated, well, the rotation along the z-axis takes into account also that. Well, then SO3 is something that we know because we were eating and digesting Se3 for so long. We could straightforwardly represent a minimal parameterization for the perturbation as a delta XR, which belongs to R3, which will be equal to a vector consisting of delta alpha x, delta alpha y, and delta alpha z. Right? This will be my parameterization. Why do we need to make this difference? Because SO3 is not a Euclidean space, and so we will also need a box plus. But the box plus is easily defined. We could define the box plus, which returns us XR prime, which should be equal to XR box plus delta XR, as something that we know. There is something I did not mention. How do we represent a state in our formulation? Well, we could straightforwardly represent it as a rotation matrix R3 by 3. This element of SO3, while the perturbation is represented by this 3 vector containing the 3 angles. Now, any idea on how to define this box plus operator? Exactly. Exactly. And we have defined the box plus. Cool. But this is only one part, right? So this part here was the robot position. Then there is the second part, which is the stars. Okay? Now, the stars are basically homotopic. They are directions, right? So now, a domain of the stars, let me call it XL to denote that they are our landmarks. To which space do they belong? Landmarks? Come on. I would say that we all agreed that the stars, to us, they only give us directions, right? And before you were insisting so much on spherical coordinates or something like that, or spherical things. But the domain of the directions is the domain of the sphere, because that's the domain. So the stars belong to the sphere. So S2. Okay? I could represent a star, the direction of a star, as a unit vector. This is not the solution, it's one of the many solutions. It's the simplest one I can think of. So, I could represent the direction of a star as a unit vector. So the domain of the directions is the domain of the sphere. Because of the star, I cannot observe the twist, the rotation along so if I look at the star and one single and I rotate along that axis, I cannot observe the variation. Do you agree? Okay, this is cool. And another thing that we could do at this point, also the sphere is a manifold. So also in this case we need to define a box plus operator. And so we need also to define a minimal parameterization. Any idea, or a parameterization for the perturbation? Any idea on how to move a point on a star? A point on the sphere so that it remains on the sphere? First of all, how many dimensions do I have? Well, the sphere is a surface, so I have 2 dimensions. But what do I put in these 2 dimensions? Just think about a point on the sphere, and you want to move it. What are the elementary motions that you can do in order to move a unit vector so that it stays a unit vector? And to move it in any arbitrary position on the sphere? Yes, radius. Not really a radius. What do you mean for radius, Hossam? Exactly. We can just put 2 angles. So we could move a point from a point on a sphere in another point of the sphere. Like we can define, for instance, an elementary motion along the z, an elementary motion along the resulting y. It's a rotation matrix, only that we need 2 angles in the rotation matrix. So, yes, and this will move our unit vector. So, then we call these alpha y and alpha z. Allow me to call them this way because alpha, so that I can say that x stays where it was. Okay? Very good. Now I have defined this element, and I'm fully ready to define the box plus. And I have done it. So like, how would you define the box plus in this case? So I would do this way. I would take the point, which is a unit vector, the direction. I multiply it exactly. I would apply a rotation along the z so that I can move no. Okay. I would apply a rotation along the z. I have a point on the sphere. I want to move it. I would first rotate it along the z vector, and then I would rotate it along the resulting y vector, and then I can move it wherever I want. Me upside down. Let's see. And that's exactly what I've written here. I take my direction vector, I rotate it along the z-axis of the perturbation along the alpha z, and I rotate it along the y for the perturbation along the alpha y. We don't need a v2t here because we already have a point, like we already have a unit vector. We just need to rotate this vector of the minimal perturbation that we apply to it. Okay. Exactly. And so this was the first part. Then the painful thing comes. The measurements. The measurements are... What are the measurements? Well, they have the same nature of the landmarks, because they are azimuth and elevation, which we know to be homotopic, to be a direction vector. So we could say that Z belongs to S2, because this is the direction at which I observe a star, which is a direction vector, from a certain orientation. So it's homotopic to S2, to the sphere. And this is Z. Now, in order to compute the box minus, because we will need a box minus at this point, it's quite painful, right? Because if we would like to have a definition of the box minus which is compliant with the box plus that we have given for the state, well, we will have to do a little bit of math, because we would have to find the pair of rotation matrices on y and on z, such that that applied to a certain orientation will return us will move us to that orientation. So namely, we would have to resolve this equation over here, where this is the position B from which we subtract, this is the position that we subtract, and then we will have to just forget about this, and we will have to find two rotation matrices such that this element is equal to this element multiplied by these two boys. Once we have found these two rotation matrices, we extract alpha y, we extract alpha z, and then we have our box minus. This in case we want to be perfectly compliant with the definition of box plus. Okay? So we have to do quite some calculations if we want to define the box minus. But we could say that this is our first definition. So like we can say that z prime box minus z is equal to alpha, a pair alpha y and alpha z, such that z prime, z prime is equal to r of alpha y, ry Ry of alpha y times Rz of alpha z multiplied by z, where z belongs to S2 and it has the same definition as before, so x, y, z, such that z in norm is equal to 1. This would be a definition of box minus. Then how to resolve this is another issue, but could work. Now, you can have fun putting the constraints of the rotation matrices, do a lot of calculations, and come back with a bunch of equations that will resolve this box minus. I mean, you know how lazy you don't know how lazy I am, but sometimes when there is something that can be done easier, I tend to do it easier. And I would, any idea on how to make your life easier in this problem? Maybe relaxing something. Now, this is the sphere. And if I pick 2 points on the sphere, which is 2 3D points, right? This one, and maybe say this one. Of course, the distance along the geodesic will be something like that. And that would be just the relative angle, this alpha x, alpha y that I would find here. Yes, makes completely sense, as I read, makes completely sense to say, you know what? I mean, I know that these are unit vectors, but I'm just interested into a delta, into a difference. And so I just like take one point and the other, and I do the chordal distance, because I know that if 2 vectors are the same, their difference will be 0, and this is compliant with an error metric. Of course, I will have it won't function that well in situations like, for instance, where I have a point in this location and a point in this location, because the chordal distance will return me a vector, a gradient along a direction that goes inside the sphere, while a proper chart will return me a gradient that rotates around the sphere to go to this thing. But as long as I am in a neighborhood, I'm fine. I would say that the chordal distance is more or less, is very close to the geodesic distance. Or at least it's not. Okay? So, straightforwardly, alternative. In this problem. Chordal distance will simply mean ignore the minus, the box minus, like treat these unit vectors on the sphere as if they were regular vectors. Okay. Now we are done with the domains, and what we need to do is to calculate the prediction function. We are in a least square setting. What would be the prediction? So if let's say my star XL, sorry, assuming I know the location of a star, XL, and I know the location of the robot, XR, where will I observe the measurement, Z? Where will I observe this star? The location of a robot is an orientation. So my goal is to do this is measurements. and this one here is measurement function. H of x, right? So how to answer this question? Well, assuming that I am at a certain orientation and I see and there is a star in that direction, at which direction will I see in my local reference frame the direction of the star? That's how to answer the question. It's equivalent to the how to determine the projection of a landmark, only that you get rid of the translational component. So let XL be the position of the robot in the like with respect to the origin, and if there is a direction vector which points somewhere, well, the Z, I made a construction here to elevate the writing plane that makes it not really handy. Right? Like, if this is the direction at which a star stays, and if I am located in a certain position, then in order to express this direction in my own reference frame, I just have to apply the inverse rotation to the direction of the star. And then I've done my prediction. I can also write it nicer because I know that this is transposed. Okay? And then, if we use the chordal distance, then the error function will be simply equal to h of xr xl for a pair robot landmark, but we have many of them. Does it sound reasonable? Okay, we're nearly done. Let's see. The other part of the size of the Jacobians, right? So I need another piece of paper. Assuming that I have, right, now can you see? Sorry guys. Yes, you should be seeing now. Okay, and then I've concluded the first part of my least square definition. I'm not completely done. Of course, I mean, you have to tell me what is the state, what are the Jacobians, and so on and so forth. What, not what's inside. Okay, I will not ask you to calculate the derivatives. And another thing that might be interesting is the Jacobians. Now, assuming that I have n robot positions, so error function. One generic, like my state will be consisting of many robot positions and many stars. Let's say that I have n robot positions, so state, and I observe m stars. Each robot position belongs to SO3, and the delta x is belongs to R6. And I have m stars. Each star belongs to S2, and the perturbation vector of a star, the delta x L, belongs to R2, because we have only two angles. I think you can see, yes. No? Okay, so the total perturbation vector will be consisting of how many blocks of dimension 6? Exactly. So the structure of my perturbation vector will be a large thing containing n blocks of dimension 6 and m blocks of dimension 3. The generic Jacobian between arising from a measurement of a robot to a star will therefore be a matrix that, how tall is it? So J I J, where I is the robot position, robot index, and J is the star index. You can't see, or you can see, because okay. What is this size? Let me put right, sorry Andrea, because I'm so, like, I made a mistake. It's not in R6, it's in R3. Yes, thanks for correcting me. I made a mistake. So we are not talking about the translational component, we are only talking about the rotational component, and we decide delta XR, according to our definition over here, as dimension 3. So it was a mistake of me. Okay? Exactly. So we have, okay, so the total size, okay. And how tall should the Jacobian be? What is this one over here? What is the dimension of a measurement under the chordal error function? What is the dimension of this object? This error is a direction, right? If we use the Manuel says 2. If we use the manifold is 2. If we use the chordal is 3. But yes, it has the dimension of the measurement. Of the error, sorry. So if we use the box minus, this error here has dimension 2. If we use the chordal, this error here has dimension 3 because it's the difference between two unit vectors. Exactly. Coherent? Very good. So this is 3. And then here I will have to have a dimension which is coherent with this one over here, which is 3n plus 2m. And this is 3 or 2, depending on whether you use the manifolds or not, the box minus or not. Let's say that we use the chordal because it's much simpler to implement. Okay? Now, the structure of the Jacobian will therefore be, now I expand it, Jij is equal to the Ej we have to conduct the derivative of the error function evaluated in delta x equals to 0. Now, the box plus we straightforwardly extend to the whole stack, and so the box plus in this problem will be applying the perturbation of each field to the respective field. And the Jacobian, given that this delta x here has dimension 3n plus 2m, so it's very large, but will be also large, but not all the variables that are in here are active in the Jacobian, namely only the variable I and the robot position I and the landmark j. Therefore, assuming that we have this ordering over here reflected, or assuming we need to have it reflected into the Jacobian, then we will find that I will have how many non-zero blocks? It's not necessarily symmetric, but This is a little bit smaller. Well, if I derive the error function of the eth robot position and the jth landmark, so with respect to any of the variables which is not the robot position or not the landmark, I will straightforwardly have 0. So I will have non-zero blocks only in this location and in this location. And this location here is a 3 by 3 block, or 2 by 3 block, depending on which definition of the error I use. And this location here will be a 3 by 2 block, because in here I have the delta x ri, and here I have delta xlj, and this width here has to be 3, and this width here has to be 2, because delta xl is big 2 and delta xr is big 3. And in particular, in this location over here, I have the Aej of xr box plus delta xr comma I xlj derived with respect to delta xri evaluated in 0. Given that I'm differentiating with respect to delta xr, I don't need to put the box plus in here. Box plus in here. And then in this block over here, I will have the Aij of xr, comma xl, xri, xlj box plus delta xlj derived with respect to delta xlj evaluated in delta x equals to 0. Okay? Then I have fully qualified my problem, right? There's nothing else that I have to... The rest is mechanics. The second question of the exercise was asking, draw me the block structure of the H matrix for a typical problem. Now, I can do it straight away, assuming that this is a factor graph where those represent robot positions. Those represent star positions. These are stars. And these are robots. So this is X, L, XR1, XR2, XR, R3, XR4, XR5, XR6, XL1, 1, X, I have to decide where to put this index, XL2, XL3, XL4, XL5. And let's assume that from here I observe this and this. Okay, so I have this pattern of observations. I'm drawing it in a factor graph fashion, so I have to put a box inside every measurement. And this box here will contain actually the measurement that this robot does with respect to this star. Okay. Now, considering this history of the robot, can you dimension the H matrix? Of course. And can you decide which blocks are full in the H matrix? Of course. So first of all, the H matrix will be consisting of 6 blocks for the robot position. The perturbation vector will be consisting of 6 blocks for the robot positions and 5 blocks for the star positions. Okay. So now, keep it in mind. I will bring it back upon you. So, my state vector is quite large. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, and 5. These are robot positions, and these are landmark positions. So I will have to repeat it. 1, 2, okay. And now the challenge of making lines straight. But for this usage, I will use a thermometers. Haha. I would have been smarter if I was drawing first the outer box, but I would survive. Okay, now this is the factor graph, and this is the pattern of the matrix. Of course, given that it has to reflect the structure of the state vector, we could immediately say that this part over here will be characterized by blocks that have a certain dimension. What's the dimension of these blocks? So these are robot positions, and these are star or landmark position. And the same applies here, right? So what is the size of one of these blocks? These are the outcome of a product of a 2 by 2 things, right? So this will be 2 by 2. These, they are, this variable here is dimension 3, dimension 3, dimension 3, and so on and so on. So all these blocks here are 3 by 3. These blocks here, well, they have to be dimension 3 times dimension 2, because otherwise the columns will screw up. And this is the transpose of this. So 2 by 3. Okay? And similarly, and now, what is the structure of the matrix? Well, for sure I will have full diagonal, because all variables are involved in some measurement. Then, what is the contribution of this measurement between the first robot position and the first landmark position? Well, remember the H blocks, right? First robot position, first landmark position means that I will have a non-zero block here, a non-zero block here, a non-zero block here, because it's decimmetric. What is the contribution of, let's say, this measurement over here? So, robot 4, landmark 4. Well, I will have non-zero in position 4, non-zero in the other position 4, and also in the symmetric one. And here I have already made it dirty. So like you continue in this way, you fill in and you discover the sparsity pattern of the matrix H. Okay? Yes? And then I think we still have 20 minutes. Well, and this resolves, let's say this way, this additional exercise. Now, if you want, I can scan these pages and put them in some way available to you for in the repo, so that you don't have to watch the video if you want just to check something quicker. Now I would say let's see each other on Zoom. Give me 3 minutes and then I will be with you. In the next lesson, upside down. Okay. In the next lesson, we will have the whole lesson on Zoom, so that if you have to ask anything, you just show up. And we will also try to do, if you get an idea on the project assignment, we will also start taking the assignments of it directly in person or in Zoom. See you on Zoom.